Welcome to video 1 for chapter 12 for AP Statistics. This is actually our first unit in AP Statistics. Chapter 12 is on sample surveys. Remember, we're focusing on producing good data first, and then we will learn how to work with the data. Okay, the first big idea with sampling and surveys is actually drawing the sample. That may sound kind of evident, but it is the first concept. But let's think about, what do we really want? We want something about an entire population of individuals. Maybe we want to know the average income, the mean income to be specific, of all U.S. college graduates. Why don't we do that? Why don't we just interview every college graduate, find out how much they make, and take the average? Well, that's impractical, if not impossible. So what do? We examine a sample, a smaller group of individuals selected from the population. So we do get a sample of U.S. adults who are college graduates, and we find out how much they make. And hopefully our sample will be representative of our population, and so we'll have a good estimate. This is a natural thing to do. If you want to know how a pot of soup that you're cooking is going, and you want to make sure everything tastes all right, you just take a small little spoonful to taste it. You don't have to taste the whole entire pot of soup. An example of sample surveys are opinion polls. The sample must be representative of the population. Like I said, in order to really know anything about the population, the sample must look like the entire population, but just on a smaller scale. If not, the sample can give misleading information about the population, and professional pollsters really go to a lot of efforts to make sure that the samples are representative. Sampling methods that by their nature tend to over or underemphasize some characteristics of the population are said to be biased. Whatever you're trying to measure will then likely be off base. It won't be measuring accurately that population parameter that you actually want to know. So you need to avoid this. There is no way to fix the information if your sampling methodology is biased. How do we avoid it? We select individuals for the sample at random. Randomizing protects us from the influences of all features of our population, even ones that we may not have thought about. Okay, so randomizing means letting chance pick our individuals, and that helps in case we don't know what all the influences would be that could have an impact on the responses to our survey. So if you think back to that pot of soup example, if we know that we put a little bit of salt in the pot of soup, we know we need to stir it before we taste it. Otherwise, if we take a taste from the top of the soup, it's going to be too salty. If we took a taste from the bottom of the soup, it would not be salty enough. So we need to stir it. If someone had come in while we weren't looking and put a handful of peas into that pot of soup, when we stir it, when we randomize, we mix things up really well, and we don't know which little portion of the soup is going to be on top. Okay, we let chance determine that. Not only do we mix up the salt that we know about, but we mix up the peas that we weren't aware of. Randomizing makes sure that on the average, the sample looks like the rest of the population. Not only does randomizing protect us from bias, it actually makes it possible for us to draw inferences about the population when we see only a sample, and that's going to be critical for pretty much all of second semester. That's what we're going to be doing. We're actually going to be making inferences about populations based on what we find out about samples. Idea 3, so the first idea is we take the sample. Idea 2 is that we randomize. Idea 3 is that it's the sample size that's critical. Sometimes people think it's the population size. It's not. It's the size of the sample. And we're actually going to get into a discussion of, well, how large is large enough later on. It's the size of the sample, not the size of the population, that is critical in sampling. There is one exception. If the population is really small and the sample is more than 10% of the population, then population size can matter. We can run into an issue where our methods that we learn in this course won't work. We take advanced methods. The fraction of the population that you've sampled doesn't matter. It's the sample size itself that's important. Well, wouldn't it just be better to just include everyone and sample the entire population? I'm sure some of you are thinking of that right now. Such a special sample is called a census, and that is what the U.S. government tries to do every 10 years. It sounds like a good idea, but there's some issues with it. It can be really difficult to complete a census. Some people are just really hard to find. The measures are difficult to attain. Sometimes if you make a census, you destroy your population, and that's a problem. If you are taste testing, chips for Frito-Lay, and let's say you're doing Fritos, and you eat all the Fritos, if you do a census of every Frito for quality control, well, then there's no Fritos to sell. So that would definitely be a case where it's just pretty impossible to complete a census. Populations rarely stand still. Like for humans, there's always people who are being born, there's people who are dying, there's people who age out of age categories. It's just really hard to get everybody that's in a population and measure whatever it is you want to measure and not have anybody enter the population or exit the population. And it can just be more complex than sampling. When the U.S. Census occurs, a lot of times college students are counted twice, once where they live at college and once by their parents at home. So it's just much more complex than taking what you know to be a well-representative sample. Okay, so we keep talking, and I mentioned that there's something about the population we want to know. That something is called a population parameter. Okay, it's a characteristic, a variable about the population we want to know. Okay, there's a specific piece of information that characterizes the population and we want to know it. Well, we're not doing a census, so we can't know it exactly, so we want to estimate it. And our estimate that we get from our sample is called a sample statistic. These are critical concepts. You have to know what a population parameter is, and you need to know that a sample statistic is an estimate of the population parameter. For notation, we have to differentiate, okay? A mean is a very common characteristic we wish to know, and so we have to have one symbol for the parameter and one for the statistic. Now, typically, but not always, Greek letters denote the parameters and Latin letters denote the statistics. So for the mean, usually Y bar or X bar, your calculator actually uses X bar. Most books use X bar, but our book uses Y bar. Either one is fine, is for the sample mean. The parameter that it's estimating is mu, okay? Mu. And that is a Greek letter right there. Standard deviation, the parameter we want to know is baby sigma, lowercase sigma, and the statistic for that is S. Correlation, we'll talk about when we get to bivariate data, and rho is the parameter, R is our statistic. Again, when we get to bivariate data with two variables, so linear regression, beta is going to be our regression coefficient, and B is going to be the statistic. And then where our book and many people differentiate from this pattern of Greek letters and Latin letters is with the parameter for proportion. Now, if we followed suit, and some books do, we would have pi for our parameter, but we don't. Okay, we have P, just the regular letter P, because pi is that, in math circles, pi is that lovely irrational number related to circles. And so in order to not be confusing, many statistics textbooks use P for the parameter. Well, we got to do something different to the statistics, so we put a hat on it. It's called P hat. And that's not just my, cute Mrs. Brown way of saying it. That's really what it's called. It's called P hat. Okay, so to be useful, statistics we compute must come from a representative sample. The sample should look a lot like the population, except just smaller. Okay, all the characteristics should be proportional in the sample as they are in the population. So how do we get a representative sample? Well, the golden standard for statistics is to do a simple random sample. For a simple random sample, we will insist that every possible sample of the size we plan to draw has an equal chance to be selected. This also means that there's an equal opportunity of selection for each individual, but also an equal opportunity of selection for each combination of people or individuals as well. And again, like I said, it's golden standard. It's the standard against which we measure all other sampling methods. But notice that it's a simple random sample. We use chance. Okay, there's no pattern to how we choose the people. We can write names on pieces of paper, put it in a hat, mix it up, draw them out. We can use a random number generator to do our selection for us. But chance is involved in the selection process. So first things first, we need to have a list of individuals in our population. Our best approximation of this list of all individuals of the population is the sampling frame. And that's the list from which the sample is drawn. Then you're going to select your individuals. Again, use the hat method, random numbers, etc. We're going to repeat, when we have repeated samples drawn at random, generally they're going to differ from each other. Okay, they're going to differ from each other. Not differ, they're very polite. No, they're going to differ from each other. These differences lead to different values for the variables we measure. And this isn't a problem. We expect it and we bring it into our methods. When we call the sample-to-sample differences sampling variability, some people call it sampling error, but that makes it sound like you've done something wrong. And so really the better term is sampling variability. So let's look at an example on page 274. So if you want to turn there, go ahead. There are 80 students in an introductory statistics class. You are to select a simple random sample, an SRS, of 5. And notice SRS is used only for simple random sample. In a little bit we're going to talk about stratified random sample and systematic random sample, but SRS is for simple random sample only. Okay, the hat method. Easiest method to use. We're gonna use it in class all the time. You're gonna write about it a lot in answers to problems. You write down each student's name on identical pieces of paper. Put them all in a hat, mix well, and draw out 5 names without looking without replacement. So without replacement means you don't look at a name and then write it down and then put it back in the hat and mix again. You wouldn't want to do that if you're trying to pick out 5 individuals from a class. You want 5 different individuals. Or you can assign each student a number, 0, 1 through 80. Got to have the same number of digits for each person. So one person would be 0, 1, another would be 0, 2, 0, 3, all the way up to 80. And use the table of random digits. There's one in the appendices in your book. And also, if I've given you your little AP statistics packet, there's one in there. Take digits 2 at a time, ignoring 0, 0, and 81 to 99 and repeats. Keep selecting until 5 individuals have been selected. So let's use the digits provided in the example in your book. So we've got 051662930577482. So student 05, we start selecting digits 2 at a time. So 05, that's in our range, so that person's chosen. 16 is in our range, so that person's chosen. 62 is in our range, so that person's chosen. 93 is out of our range, so we ignore it. 05 is a repeat, so we ignore that. 77 is in our range, and then 48 is in our range, and that's all the people we need. Or you can assign each student a number 1 through 80 and use your CAS to generate integers between 1 and 80. You will still need to ignore repeats. So go ahead and grab your CAS, go to your scratch pad, press menu. Okay, this is related to probability, so you're going to choose probability. We're wanting to produce a random integer, so we're going to choose random and then integer. In the parentheses, you're going to enter 1, 80. Make sure you put the comma. And then press enter and keep pressing enter until you've selected 5 different students. Okay, awesome. Okay, that's it for video 1. I will meet back with you in just a minute with video 2.